Introductory computer science requires a structural reorganization of a learner's problem-solving methodology. The student must transition from natural language thinking into the strict constraints of algorithmic logic. High dropout rates in programming programs are frequently attributed to a lack of student effort. However, the root cause is often a misalignment between instructional design and the biological realities of human cognitive architecture. When students encounter dynamic, high-level languages like Python, their primary bottleneck is working memory. The brain can only process a limited number of new abstractions, like dynamic binding or namespace management, at once. Presenting syntax without managing this biological limitation triggers systemic failure. The learner's working memory becomes saturated, preventing the encoding of new logic. Successful programming education requires the instructor to act as a deliberate manager of cognitive load, prioritizing the learner's processing capacity over the mere delivery of information. We analyze mental effort through cognitive load theory, categorizing working memory into 3 types: intrinsic, extraneous, and germane. Intrinsic load represents the subject's inherent difficulty, like tracking variables. Extraneous load is effort wasted on poor instructional design. When this spikes, learning stops. The goal is to maximize germane load, the productive mental energy the brain uses to build permanent neural schemas and pattern recognition. To achieve this balance, we utilize a meticulously sequenced 8-module curriculum. It is designed to minimize friction and focus the student's remaining working memory on core programmatic fluency. This pedagogical ordering is an empirical necessity. Logical sequences introduced in foundational modules act as strict mathematical and cognitive prerequisites for the more advanced abstractions that follow. The IPO model establishes software as a predictable, linear pipeline. To manage state within this pipeline, the curriculum introduces variables using a physical box analogy. A labeled container holds a distinct value that the program remembers during processing. While this container concept is technically limited for Python's specific memory model, it serves as a necessary bridge. It connects the learner's understanding of physical reality to digital state management while keeping the initial intrinsic load low. Module 2 moves to strings, introducing data manipulation through built-in features. Here, the learner encounters a shift in counting logic, zero-based indexing. Mapping the first character to the integer 0 forces the brain away from standard human counting. Adopting this mental model early builds the cognitive plasticity required for all subsequent tasks involving arrays, lists, and memory management. Module 3 introduces branching control flow and Boolean conditions, significantly increasing the complexity of the learner's mental model. Abstract relational operators are grounded in visual analogies. A traffic light represents a conditional branch, permitting the code to run only when the condition is green or true. This schema expands to if-else and elif structures. These boss statements require the student's working memory to track multiple potential execution paths simultaneously. Module 4 introduces iteration. Empirical evaluations using large language models demonstrate that sequencing loops immediately after logic scales difficulty more predictably. Applying mastered Boolean logic to a while loop requires little new schema. The traffic light simply becomes a continuous checking mechanism. Isolating loops for complex lists allows the student to master state transformation and logical stamina without being overwhelmed by the spatial complexities of memory allocation. This curriculum is built on Jerome Bruner's spiral curriculum model. It relies on the iterative revisiting of topics, where each encounter introduces a higher level of complexity to solidify the learner's mental schemas. Module 6 applies this spiral approach to lists, synthesizing variables for Module 1, zero indexing from Module 2, and iteration from Module 4 into a single, cohesive architecture. The simplistic box analogy for variables is formally dismantled. The student must upgrade their mental model to reflect how Python actually handles memory. Python's runtime behavior differs significantly from statically typed languages like C. To prevent flawed analogies from collapsing later, the curriculum aggressively shapes a model based on dynamic name binding. This introduces references. The learner is taught that variables are names bound to distinct objects. The visual evidence shows 2 distinct names, A and B, pointing to the exact same list. Mutating the list through one reference reflects in the other. Without this mental upgrade from boxes to references, students will be unable to predict the behavior of mutable data structures, leading to significant logical errors. Module 8 serves as the culmination of the sequence, transitioning the learner into the object-oriented programming model. This module demands the highest germane cognitive load. Students must synthesize disparate components from every previous stage. Under this new terminology, variables from Module 1 become object attributes, and functions from Module 5 become object methods. By reaching this level, the student is no longer just writing scripts. They are constructing complex, custom data types from first principles. Establishing an 8-module sequence is only the first step. Educational curricula are living code bases that must be rigorously maintained to prevent decay. One major risk is forward dependency creep, where advanced computational concepts inadvertently leak into foundational modules before a student is ready for them. This happens when an instructor's automated error message in a logic module uses complex list comprehension syntax to explain a failure. This violation of cognitive load constraints overwhelms the learner. It forces them to parse syntax for which they have not yet developed a mental schema. To protect the learner, modern frameworks should utilize automated pipelines to validate the curriculum. These systems can flag cross-module dependencies that violate the strict prerequisite ordering of the sequence. The success of teaching Python relies on sequence, pacing, and the relentless management of cognitive load. Adhering to this pedagogical architecture prevents rote, mechanical mimicry. It transitions students from confused typists into highly capable software architects.